how to design this then, what that means that it has to be small and it has to be acceptable. The cross-section of the core will be directly proportional to the current we want to have on the primary side. And it will also be proportional to the load we are going to put across it. But it will be inversely proportional to the Kw here is the coefficient of a waveform. For sine will be 444. And we have flux density, so it has to lower below the saturation. We have frequency and we have number of turns. And we can immediately see that the higher the frequency, the smaller the core can be. And the more turns, the smaller the core can be. And the higher the flux density, we can operate it at. Again, we can shrink that size. So it will some of those factors will be driven by material we use. If we use material which saturates at lower flux density, we have to use a bigger core. Another very important factor is that the inductance or reactance of the secondary coil has to be much, much greater than our load. If that condition isn't met, something called self-integration will not happen. And I mean, obviously this is impossible because we have omega involved anyway. But that drives basically linearity of our transformation. So our inductance is directly proportional to the number of turns. So we can see that we can improve operating conditions if we increase number of turns for the same load called burden here. Our R2 in this equation means basically any other resistance in the circuit, and I will also say something about that in a second. There are some other conditions that losses will one of the things that losses will affect, it will be the phase shift. And for example, for metering applications, the phase shift has to be very low in order to measure the energy correctly. Hence, there are some other conditions which drive what sort of values they be. You can see that some of these values are interlinked, and changing one immediately impacts something else, and that has to be very carefully designed. The resistance of the burden, which is the resistance which is connected across the secondary coil, is directly proportional to sensitivity. The greater that resistor is, for the same current, the greater voltage drop will be. So it's easier to measure small currents. But because it's involved in the first equation, we can see we cannot just change it like that infinitely, because that will mean changing the dimensions of the core. And obviously the resistor, the current transformer has to be always operated with secondary circuit closed. Otherwise, it is just step-up voltage transformer. So very, very high voltages can be generated in the secondary circuit, and that might be dangerous, which also has to be taken into account in the design, which again I'll explain in a second on an example. There are a number of performance factors which have to be taken into account. Some of these are defined by international standards, some others are driven by other requirements. There are sort of three main application areas. It's for metering, it's for protection, and it's for other instrumentation. As I mentioned about before, for metering, the phase shift and the accuracy has to be spot on, because that is very usually very accurate measurements are required. For protection, a different set of requirements is there, because the current transformers, they don't have to be very accurate, but for example, they have to withstand very high currents. So for metering, we are not expecting very high currents. The metering current transformer will be designed to operate within whatever operating range, and that is fine. But for protection, if a short circuit comes, then the short circuit current can be a number of times greater than operating current, and the protection current transformer has to withstand that. And other instrumentation, it just depends on the application. A regular current transformer with a metal core, they usually are designed up to 20,000 amps, but this also can vary. There are some other solutions which can measure currents even higher, but we are talking here about classic current transformers. The secondary current range, the standardized output is 1 amp or 5 amp full range, and sometimes other values are required, or they just cannot be met. This 1 amp. An example is, for example, electronics, where I mean just I had to put in a bag because it's so small that I would lose it otherwise. I mean, obviously, you cannot expect to have a secondary with a 1 amp full range. That's not possible. And with the current transformer which don't work in protection, operation up to 120% of rated current is expected, and that's defined by standards. And again, if it's used for energy metering, the phase shift is crucial. So it has to be within whatever value is specified for a given accuracy class. The errors. As I said above, in order to have the secondary current almost equal to the primary, we have to have certain conditions. And then almost equal is defined simply as an error. So that is defined by simply measuring the difference of the RMS values. So we can put an RMS meter on the primary side, RMS meter on the secondary side, and using a number of terms we can calculate what that error is in terms of percent. Then there is the phase error, which is basically the phase difference between the primary and the secondary signals. It doesn't, the amplitude doesn't matter, it's just the phase of that, for example, sinusoidal signal, but it doesn't have to be sinusoidal, because there's also something called composite error. That's a bit confusing because the first one is difference of RMS values, but the composite is RMS value of difference. And the way this is done is the primary current waveform is taken, and then the secondary current waveform is taken, and using the correct ratio of turns, they are just subtracted. So the two waveforms are subtracted from each other, and we're looking at the RMS of that. And this is mainly important in where non-sinusoidal waveforms are involved. So we can see whether, for example, if we have a square waveform of current, is that waveform being reflected well on the secondary? Is it not distorted in a different way? And if it's perfectly square, we will get zero error. But if it isn't, if the transformation is not done correctly, then we will see some error. Obviously, for sinusoidal waveforms, the composite error and the current error will be, by definition, the same if we work out the equations. Industrial current transformers. It's just a few examples of these. You can see that our red clamp here, that's one of our examples of a clamp-on current transformer, but there are others. And not all of these I could bring. You can also see the small one in the bag. I mean, that's a very, very small, but it is practically the same device. It's a current transformer. Specifically, I couldn't bring the one on the right, the upright, and you can sort of wonder, that doesn't look like current transformer really. And you have to look at under the bonnet to see that it is exactly that. And that's what it is. The main chunk of this is just insulation, because this is used in high power, high voltage systems. Sometimes it's called a hairpin because the primary conductor sort of comes at the top, then runs all the way down and comes back at the top. And the current transformers, the magnetic cores, sit just at the bottom. And because this device is very expensive, because the insulation is very expensive and it is usually oil filled, by making such current transformer, you usually would see a number of magnetic cores sitting inside. Some of them would be for metering, some would be for protection, some may be for some other instrumentation. And you can see that there is, in this case, 5 cores sitting there, each of them are designed to do something else. We have something which is, for example, called Rogowski coil, which can measure very high currents, I mean thousands of amps easily. But it's not a current transformer. It is a sensor. It doesn't have a magnetic core. It's still, there is an induction of voltage involved, but one of the conditions which isn't met is that the load in here is much greater than the impedance of the secondary. And as you might remember, it should be the other way around for a current transformer. This, therefore, cannot self-integrate that current. So any distorted waveform, it cannot be measured just like that. And there's a black box involved there, which basically performs analog integration, and only then that signal can be measured. The other one, the one in the middle, is a specific sort of current detector, and it measures currents quite precisely, but there are no core is involved, no secondary winding. They're just sensors arranged around that, so there's not even the core is, whatever it's there is not even clamped around a wire. It's just a number of sensors which process the information in a specific way. And there are a number of other current detectors, like for example with a split core, where a sensor is put inside a core, and either this can be in passive or in active mode, and just that sensor detects what is the magnetic field in that core, or maybe drives that core with some other waveform. But again, this is not a current transformer device. It's a current detector. I mean, in here, you cannot even define what the burden is, really. And one of the advantages is that we can measure DC current with it, but it is not a current transformer.